Hello, my name is Adrienne, and today I'll be your instructor for Introduction to Mechanics. So today's learning objectives are to 1. Define engineering mechanics, and 2. Analyze rigid bodies using vector notation. So what is engineering mechanics? Engineering mechanics is the study of an object, typically rigid bodies or frames, such as the box shown, and the forces acting on the body. So any object has the force of gravity acting on it towards the surface of the earth. So this box itself has the force of its weight acting downwards. However, this box is not falling to the surface. Therefore, there's a reacting force acting normal to the surface that is opposing the weight of the box. So engineering mechanics we're going to define as a study of external forces acting on a rigid body and the effects of these forces on the motion of the body. So engineering mechanics has two separate divisions. There's dynamics and statics. Dynamics is the study of accelerated motion of bodies. So this is the study of moving cars, maybe the gears in guns, or an object falling to the surface of the earth. Now statics is the study of bodies in equilibrium. Now, which division do you think civil engineers are more focused on? Yes?
Is it statics because everything, like bridges, are stationary?
Exactly. So civil engineers are concerned with statics because all of our designs are built such that they're not moving. They're in equilibrium. So what exactly does equilibrium mean? Equilibrium means that the sum of the forces equals 0. So the sum of the forces acting in the x direction equals 0. The sum of the forces in the y direction equals 0. Which also means that the sum of the moments equals 0. So who knows the equation for moment? Yeah?
Force times distance?
Exactly. So moment equals the force times the distance. So if the sum of the forces equals 0, then the sum of the moments also equals 0. So the sum of the moment of a force equals 0, and however, if a force is acting in the direction of the point load of the point itself, then the moment cancels out and does not have an effect on the moment. So forces are the interaction of two bodies. A force is a vector quantity with magnitude and direction. So a force itself can be broken up into two component vectors of its x and y, or its x and y components can be added together to find the resultant force. So now, what causes forces on a body? Does anyone have any guesses? Okay, no worries. So the forces acting on a body are the end supports, the loading on the rigid body, and also the self-weight. So end supports can be rollers that have a force acting only in the y direction. There's pins with forces in the x and y direction. And there's also fixed joints with a x, y, and also a moment on the support. So loadings, there's several different types as well. You have your point loads, which are a force acting directly on a point on the rigid body. And we also have distributed loads with the units of force per length. So distributed loads are several different types. There's rectangular and there's also triangular. And so a rectangular distributed load, to solve, you're going to figure out what the resultant force is. So the resultant force is the area under the distributed curve with the resultant force acting at the midpoint or the centroid. So for a rectangle, it would be the area of the rectangle, which is the distributed load times the length of the distribution acting at the center. Now for a triangle, it would be the area under the triangle. So 1/2 the distribution times the length, and it's acting at the centroid, which is 2/3 from the endpoint. So now let's actually get to analyzing a rigid body. So right now we're going to look at the Golden Gate Bridge. So the Golden Gate Bridge has the bridge deck, and there's the forces acting on it. So who wants to take a guess at one of the forces acting on the Golden Gate Bridge? Yep.
The cars that are driving on it?
Yeah, definitely. So we have the cars, we have the self-weight, and we also have the supports that are going to cause forces onto the bridge deck itself. So we have the forces from the supports, we have a distributed load from the self-weight, And we also are going to look at a car, a point load of 1 car. So let's actually get some pen and paper out, and we're going to do this calculation. All right, so right here we've simplified the design of the Golden Gate Bridge into a simple free body diagram that we're going to analyze for to calculate the supports or the reactions at the supports. So right here we have the bridge deck of the Golden Gate Bridge and the 2 supports. So we have a joint pin support, and we also have a roller support. So these supports are going to be 500 meters from the end, and they're going to span in the center 1,000 meters. So now we have the distributed load of the self-weight of the bridge that runs the entire span. And this distributed load has a magnitude of WU, which is going to equal 100 newtons per meter. Now we're also going to look at a 500 Newton car placed directly at the center span of the bridge. So right at the center we have a point load of 500 newtons. And we also want to look at the supports, the forces at the support, which are what we're going to be solving for. So we're going to call this pin support A, and we're going to call this roller support B. So we're going to solve for AY, because it's in the Y direction, and we're going to be solving for BY. So the first step is we're going to turn this distributed load into a point force. So the distributed load of 100 newtons acting across the entire 2,000 meter span of the Golden Gate Bridge is going to give you a resultant force of force WU, and it's going to be the area under the distributed load, which is going to be 100 newtons per meter times the 2,000 meter span of the bridge, which is just the 500 plus 1,000 plus 500 meters. And that's going to give us 200,000 newtons. So let's actually draw in this resultant force on top of this other point force. So this is going to be 200,000 newtons. So anyone want to take a guess at what the first step in analyzing this system is? Yep.
Is it to set all of the forces add them together and equal 0?
Exactly. Yep, so let's look at one direction at a time. So first we'll look at the x direction. So the sum of the forces in the x direction equals 0. Now, are there any forces in the x direction?
No, they're all in the y direction.
Great. So the sum of the forces in the x direction equals 0, and there's 0 forces, so we're already set. We no longer have to look at the forces in the x direction. Now let's look at the sum of the forces in the y direction. So let's also set a positive direction for the forces. Let's say upwards is positive, just because that's the convention that we use in most graphing systems as well, and in vector notation. So the sum of the forces in the y direction equals 0. So what are some of the forces acting in the positive y direction?
AY and BY.
Exactly. So we have AY plus BY. And then in the negative direction, we have the 200,000 Newton force from the distributed self-weight load. And we also have a negative 500 newtons from the weight of the car, the point load of the car. So let's actually solve this equation for AY. So we're going to say AY is going to equal 200,500 newtons minus BY. So now what's another force equation that we can use to solve for BY? Yep.
The moment equation?
Exactly. So let's take the moment around A. Does anyone want to take a guess at why we're going to take the moment around A as opposed to at the end over here? Yep.
Is it because if you take the moment at A, then it will cancel out that force because the distance is 0, so then it'll make it easier to do the rest of the calculations?
Exactly. If we calculate the moment around A, it cancels out this force at A, and the only two forces that we'll have to solve for are the forces, or the only two forces we'll have to take into consideration are the forces from the distributed load and the point load, and also this force By. So we'll actually be able to solve for By. So the sum of the moments acting at A equals 0. So let's also set a positive sign convention of clockwise. So clockwise in this equation is positive. So at the moment A, we have the forces of the distributed load and the 500 Newton car that would turn the system in a clockwise rotation. So that's going to be a positive 200,500 newtons acting at a distance of 1,000 divided by 2 because it's at this mid-span, so 500 newtons. 500 meters. And then we're also going to have a counterclockwise rotation from By that's going to be By times 1,000 meters. So when we do this out, let's actually solve the equation. So we'll have By on one side and the forces on the other side. So we have By times 1,000 meters is going to equal this 200,500 times 500 meters, which you guys can do out if you have a calculator, or you can trust me in that it is 100,250,000 Newton meters. So then if we solve for By, we get that By equals 100,250 newtons. So now we solve for By, and we can plug it back into this equation up here, and we get that Ay is equal to 200,500 newtons minus By, which is this 100,250 newtons, and we get that Ay also equals 100,250 newtons. Now if we want to go back and check our equation, we can plug Ay and By into the sum of the forces in the y direction equation, and if we get 0, we know that we solved it correctly. Or we can also go and solve for the moment, say at this end location or this end location or any location within the system, and we should get that the sum of the moment equals 0. However, I think that's all we have for today. If you have any questions, please feel free to contact me after class or come to my office for questions. Thank you very much.